You know, they're kind of the invisible giants of our world. Massive steel islands, silently hauling hundreds of thousands of tons of oil across our oceans, powering our entire economy. But have you ever stopped to think about what's actually going on inside one of these supertankers? I mean, how do they safely carry what's essentially a flammable ocean? And what kind of incredible engineering keeps the whole thing from going wrong? Well, let's dive in and pull back the curtain.
All right, here's what we're going to cover. We'll start with just how massive these things are, the biggest movers on the planet. Then we'll dissect the anatomy of a tanker, look at its circulatory system of pipes and pumps, and get into the really clever science they use to control the immense danger. We'll also see how they measure what's invisible inside the tanks, and finally, how they work to protect the planet.
Okay, first things first, let's talk scale. When we say the world's biggest movers, we're not kidding. These ships are basically floating pipelines. They're the critical link connecting the big energy exporting OPEC nations, thanks Saudi Arabia, with the world's hungriest consumers like the US and China. Their enormous size isn't just for show. It's a direct result of global demand engineered to move the most product for the least cost.
So how do we even measure that kind of capacity? Well, it's done in something called deadweight tonnage, or DWT, which is basically the total weight of everything a ship can carry. You've got different classes like Panamax or Suezmax, which are pretty cleverly named for the canals they can barely squeeze through. But then you look at the bottom of this list. VLCCs, very large crude carriers, and ULCCs, ultra-large crude carriers. We are talking about ships that can carry over 500,000 tons of oil in one trip. Just try to wrap your head around that for a second. It's absolutely staggering.
So how in the world do you design a ship that has to be both a gigantic container and a floating fortress of safety? Let me tell you, it is way more complicated than just a big metal shell. The whole design is a masterclass in squeezing in every last drop of cargo while building in layers upon layers of safety, a lesson the industry learned the hard way.
And here's a perfect example of that, the move from single to double hulls. It used to be that just one single layer of steel separated all that oil from the ocean. You can probably guess how that went. After a few absolutely catastrophic oil spills, international law stepped in and mandated a double hull design for all big tankers. It's literally a hole within a hole. This creates a protective empty space that acts as a giant crumple zone, a crucial safety buffer if the ship gets hit or runs aground. It's a game-changing piece of engineering born directly from environmental disaster.
And on the inside, a tanker isn't just one big bathtub. No way. It's more like a complex honeycomb of specialized compartments. You've got your main cargo oil tanks, of course, but then you also have segregated ballast tanks. These get filled with seawater to keep the ship stable when it's not full of cargo, and by law, their piping is completely separate from any oil system. You've got slop tanks to collect oily water after cleaning, and you've even got these empty spaces called cofferdams that act like fire breaks and safety gaps between different tanks. Every space has a purpose.
Now, let's move on to what you could call the heart and arteries of the whole operation, the mind-bogglingly complex web of pipes and pumps that are responsible for moving hundreds of thousands of tons of liquid cargo around safely and efficiently. And this is where you can really see how a ship's job shapes its design. On a huge crude carrier, a VLCC, you'll probably find a direct line system. Think of it like a superhighway. It's simple, it's fast, and it's built to move one thing, crude oil, as quickly as possible. But on a product tanker that might be carrying gasoline, diesel, and jet fuel all at once, that's where you find a ring main system. It's more like a complex city grid of pipes. It gives them total flexibility and, most importantly, makes sure that none of those different valuable cargoes ever get mixed up.
So what's at the heart of this whole system? The centrifugal pump. The idea behind it is actually pretty simple, but the scale is just immense. First, a spinning part called an impeller creates a vacuum which sucks the liquid right out of the cargo tank. Then, that same impeller gives the liquid a massive shove, imparting a huge amount of energy to it and blasting it out under high pressure into the pipelines on deck. Okay, we've talked about the mechanics, but let's be real. The single biggest challenge on a tanker is the cargo itself. We are literally talking about how to safely manage a floating, flammable ocean. And this is where the physics and chemistry get really cool. Right, so here's the most important thing you need to understand. It's not the liquid oil that actually burns. It's the vapor it releases. And the flash point is the absolute lowest temperature where a liquid gives off enough of that flammable vapor to mix with air and become something that can catch fire. It all comes down to the classic fire triangle. To get a fire or an explosion, you need three things. You need a flammable material, that's our hydrocarbon gas. You need oxygen from the air, and you need some kind of ignition source, like a spark. The entire safety philosophy of a modern tanker is built around one simple goal: break this triangle by getting rid of at least one of its sides. But it gets even more specific than that. The mix of gas and air has to be just right to ignite. It's kind of a Goldilocks situation. For crude oil, this flammable range is between about 1% and 10% hydrocarbon gas in the air. Any less than that, and the mixture is too lean to burn. Any more than that, and it's actually too rich. There's not enough oxygen to keep a fire going. And this number right here, this is the secret sauce. Through a lot of testing, engineers figured out that for a hydrocarbon gas mixture to even have a chance of igniting, the air around it has to contain at least 11% oxygen. This little fact is the key weakness in the fire triangle that they decided to exploit. So think about it. You can't get rid of the fuel. That's the whole point of the ship. And you can never, ever be 100% sure you've eliminated every possible source of ignition. So what's left? You remove the oxygen. It's an absolutely brilliant and elegant solution. Tankers have what's called an inert gas system that scrubs the exhaust from the ship's engines and pumps that gas, which is low in oxygen, into the cargo tanks. And just look at this chart. It shows you the incredible margin of safety this creates. See, combustion can only happen above 11% oxygen. The inert gas being pumped into the tanks has less than 5% oxygen. This keeps the atmosphere inside the tank well below 8% at all times. It's safely outside the flammable range. Problem solved. Okay, so you've made the tank super safe by getting rid of the oxygen. Fantastic. But in solving that problem, you've created a totally new one. You now have this sealed, pressurized, hazardous environment. So how on earth do you accurately measure what's inside it? I mean, you can't just pop open a hatch and drop in a giant measuring stick, right? The second you did that, you'd release a cloud of flammable gas and you'd let oxygen in, wrecking that safe, inert atmosphere you worked so hard to create. You need a way to do it from the outside, a closed system. And the answer is pretty clever. It's a measurement called ullage. Instead of measuring the liquid from the bottom of the tank going up, the crew measures the empty space from a fixed point on the top of the tank down to the surface of the liquid. This measurement is absolutely critical for business because it's how they calculate the exact volume of cargo that's been loaded or discharged. And they do it with this amazing piece of gear called a UTI device. That stands for ullage, temperature, and interface. Think of it as the Swiss Army knife for tanker crews. It's a portable electronic tape that gets lowered through a special, tiny gas-tight valve on top of the tank. And in one go, it gives you 3 vital pieces of information. The U is the ullage, the cargo level. The T is the temperature, which is crucial for calculating the precise volume. And the I is for interface. It can actually detect the exact point where the oil stops and any water that's settled on the bottom of the tank begins. Now, all of this incredible technology isn't just about protecting the ship and its crew. It's also about protecting the marine environment. A tanker's responsibility goes way beyond its own steel hull. One of the biggest issues is actually ballast water. When a tanker offloads its oil, it fills some tanks with seawater to stay stable. But that water is full of tiny local marine life. To stop ships from accidentally moving invasive species from one part of the world to another, there are strict rules. The D1 standard basically says you have to swap out that coastal water way out in the deep ocean. But the newer, tougher D2 standard says you have to have a treatment system right on board, using things like filters and UV light to neutralize any living organisms before you discharge the water anywhere. You know, this quote really just says it all, doesn't it? From the double hull to the inert gas system to the UTI device. Every single piece of engineering we've talked about is a direct result of understanding the massive risks and consequences of this business and then designing incredibly sophisticated systems to manage them. These giants are just incredible monuments to human ingenuity. They fuel our modern world with a kind of precision and reliability that most of us just take for granted. But as we've seen, keeping them running is this constant, high-stakes balancing act between immense utility and immense risk. So that leaves us with one final thought. What does it really take to keep these ships, and by extension our planet, safe?